why gravity is not a force. Let me tell you something that will sound absolutely insane. You're not being pulled down right now. Nothing is pulling you toward the floor. Nothing is pulling the Earth toward the sun. Nothing is pulling the moon toward the Earth. Gravity, the thing you've been told is a force since you were 5 years old, is not a force. It never was. And when you understand why, when you truly understand what's actually happening, when you drop a ball or stand on the ground or watch the planets orbit the sun, your entire picture of reality will collapse and reassemble into something far stranger and far more beautiful than anything Newton ever imagined. I'm Leonard Susskind. I've spent over 50 years working with general relativity. I've taught it, used it, argued about it, dreamed about it. And I can tell you with absolute certainty that the story you were told about gravity in school is not just incomplete. It's fundamentally wrong. Not wrong in the details, wrong in its deepest conceptual foundation. Let me start with the version of gravity you think you know. Isaac Newton, 1687, the Principia, one of the greatest intellectual achievements in human history. Newton told us that every mass in the universe attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. It's beautiful, elegant, powerful. It predicted the orbits of planets. It explained the tides. It sent us to the moon, and it's wrong. It's not wrong in the sense that it gives incorrect answers for most situations, for everyday physics, for launching rockets, for engineering bridges. Newton's gravity works spectacularly well. It's wrong in the sense that it describes something that doesn't exist. Newton said there's a force, an invisible hand reaching across empty space, pulling masses toward each other instantaneously. He knew this was troubling. He wrote about it. He said he could describe the effect of gravity mathematically, but he could not explain how one mass could act on another across empty space with no intermediary. He called it action at a distance, and it bothered him until the day he died. It should have bothered him because there is no force, there's no invisible hand, there's no pull. What there is, and this is what Einstein showed us in 1915, is curved space-time, and that changes everything. Let me explain what I mean by curved space-time, because this is where most popular science explanations go horribly wrong. You've probably seen the rubber sheet analogy. Take a flat rubber sheet stretched tight, place a heavy bowling ball in the center, the sheet curves, and a marble rolled across it spirals inward. People say that's how gravity works. The sun curves space like the bowling ball, curves the sheet, and the Earth rolls along the curved surface. This analogy is terrible. I mean, it's one of the worst analogies in all of physics education, and it's been misleading people for decades. Here's why it's terrible. In the rubber sheet analogy, what's pulling the marble inward? It's gravity, Earth's gravity. The analogy is using gravity to explain gravity. It's completely circular. It tells you nothing about why things fall. So it just gives you a pretty picture that secretly depends on the very thing it's trying to explain. The real story is much deeper and much stranger. And to understand it, we need to think about something that seems completely unrelated to gravity. We need to think about acceleration. Here is the most important thought experiment in the history of physics. More important than Schrödinger's cat, more important than Maxwell's demon. It's more important than any thought experiment you've ever heard of. Einstein called it his happiest thought. Imagine you're in an elevator, the cable snaps, you're falling, free falling. What do you experience? Weightlessness, your feet lift off the floor, your coffee floats in midair, a ball you release from your hand just hangs there next to you. For all practical purposes, you're in zero gravity, you're floating exactly as if you were in deep space, far from any planet or star or source of gravity. Now, here's Einstein's genius. He didn't just notice this, he elevated it to a fundamental principle. He said, this is not a coincidence, this is not an illusion. Free fall is not falling under the influence of gravity. Free fall is the natural state of motion. The person in the falling elevator is not accelerating. They are in an inertial frame. They are following the straightest possible path through space-time. It is you standing on the ground who are accelerating. Right now as you watch this, you feel your weight pressing down on your chair or pressing against the soles of your feet. You interpret this as gravity pulling you down, but that's not what's happening. What's happening is that the ground, the floor, the chair is pushing you upward, accelerating you upward, away from the path you would naturally follow through curved space-time. Think about that for a moment. The person floating in the falling elevator is not accelerating. You standing firmly on solid ground are accelerating every moment of every day. The surface of the Earth is accelerating you upward at 9.8 meters per second squared. You feel this acceleration as weight. You interpret it as a downward force, but there is no downward force. There's only the ground pushing you away from your natural trajectory through space-time. This is the equivalence principle, and it is the foundation of all of general relativity. Einstein realized that there is no experiment you can perform inside a closed room that can distinguish between gravitational acceleration and mechanical acceleration. If you're in a rocket accelerating at 1g in deep space, you feel exactly the same as standing on Earth's surface. Your coffee sits in the cup, your feet press against the floor. Balls fall when you drop them. Everything is identical, not similar, identical, because they are the same thing. The sensation you call gravity is acceleration and free fall. What you think of as falling under the influence of gravity is actually inertial motion, no force, no acceleration, just following the natural curves of space-time. Now, I need to explain what I mean by the curves of space-time, and I need to do it properly without the rubber sheet nonsense. It's in flat space-time, the space-time of special relativity where there's no gravity, objects that are not acted upon by any force move in straight lines. This is just Newton's first law extended to 4 dimensions. Straight line in space-time means constant velocity through space, simple. But Einstein showed that mass and energy curve space-time. The sun doesn't reach out and grab the Earth. The sun warps the geometry of the space-time around it. And the Earth, receiving no force whatsoever, moves along the straightest possible path through that warped geometry. In mathematics, the straightest possible path through a curved space is called a geodesic on a flat surface. Geodesics are straight lines on a curved surface, like the surface of a sphere. Geodesics are great circles, the paths that airplanes fly between distant cities. They look curved on a flat map, but they're actually the straightest paths available on the curved surface. The Earth's orbit around the Sun is a geodesic through curved space-time. From a 4-dimensional perspective, the Earth is not going in circles. It's going straight as it possibly can through the curved geometry created by the Sun's mass. There is no force bending its path. The path itself is straight. It's space-time that's curved. This is profoundly different from Newton's picture. It's in Newton's universe. Space is flat, time is absolute, and gravity is a force that acts instantaneously across distance. It's in Einstein's universe. Space-time is a dynamic entity that bends and warps in response to mass and energy. And what we call gravity is simply the geometry of that bending. It's not a force any more than the curvature of the Earth's surface is a force that makes airplanes fly along curved paths. Let me give you another way to think about this. Imagine 2 people standing at the equator a few meters apart. They both start walking due north, perfectly straight, perfectly parallel. As they walk, something strange happens. They get closer together. By the time they reach the North Pole, they're standing right next to each other. Did some force push them together? No. They both walked in perfectly straight lines. The surface of the Earth is curved, and straight lines on a curved surface converge. That's exactly what happens with gravity. 2 objects in free fall near the Earth are both following straight paths through curved space-time. Those paths converge. The objects get closer together. So we look at this and say gravity is pulling them toward each other, but nothing is pulling anything. The geometry of space-time is such that straight paths converge near massive objects. That's it. That's gravity. No force, just geometry. Now, you might be thinking, okay, Lenny, this is a nice philosophical distinction, but does it actually matter? Does it change any predictions? Does it make any practical difference whether we call gravity a force or a geometric effect? Yes, it matters enormously, and here's where things get really interesting. Newton's gravity and Einstein's gravity give different predictions, and every time we've been able to test the difference, Einstein wins. Let me give you the examples. Mercury's orbit, it's Mercury. The planet closest to the Sun has an orbit that precesses. The point of closest approach to the Sun shifts slightly with each orbit. Newton's gravity predicts a certain amount of precession due to the gravitational influence of the other planets. But the observed precession is slightly more than Newton predicts. It's about 43 arc seconds per century more. This tiny discrepancy was known since the 1850s. Astronomers were so confident in Newton's theory that they proposed a hidden planet, Vulcan, orbiting closer to the Sun, causing the extra precession. They searched for Vulcan for decades. They never found it because it doesn't exist. When Einstein completed general relativity in November 1915, one of the first things he calculated was Mercury's orbital precession. His theory predicted exactly 43 arcseconds per century of extra precession. Exactly when he saw the result, he said his heart raced. He was beside himself with joy. The curved space-time picture, the geometrical picture, gave the right answer where Newton's force picture failed. And this was just the beginning, the bending of light. In Newton's picture, light has no mass. And if gravity is a force between masses, then gravity shouldn't affect light. But wait, if we use Einstein's equivalence principle, if gravity is really about curved space-time, then light should follow the curved geometry too. Light follows geodesics through space-time. So if space-time is curved near the Sun, light passing near the Sun should be deflected. Einstein predicted exactly how much. In 1919, during a total solar eclipse, Arthur Eddington led an expedition to measure the positions of stars appearing near the Sun, stars whose light had to pass close to the Sun to reach us. The positions were shifted, the light had been bent, and the amount of bending matched Einstein's prediction, not Newton's. This was front-page news around the world. It made Einstein a household name overnight. But more importantly, it confirmed that space-time is curved, that gravity is geometry. That light, which has no mass, is nonetheless affected by what we used to call gravity because it follows the curves of space-time like everything else. Gravitational time dilation. Here is something that Newton's gravity cannot explain at all. Time runs at different rates depending on where you are in a gravitational field. Let's see. A clock at sea level ticks slightly slower than a clock on a mountaintop. A clock on the surface of the Sun ticks slower than a clock far from the Sun. This isn't a mechanical effect. It's not that the clock is broken or that some force is interfering with its mechanism. Time itself, the actual passage of time, is different at different locations in a curved space-time. This has been measured with extraordinary precision. In 1971, Hafele and Keating flew atomic clocks around the world on commercial airplanes and compared them with clocks on the ground. The clocks disagreed by exactly the amount general relativity predicted today. GPS satellites have to correct for gravitational time dilation continuously. The clocks on GPS satellites tick faster than clocks on Earth's surface by about 45 microseconds per day. If we didn't correct for this, GPS would be off by about 10 kilometers per day. Your phone knows where you are because Einstein was right about gravity not being a force. Every time you use GPS, you're using general relativity. You're relying on the fact that gravity is curved space-time, not a force. Gravitational waves, in Newton's picture, gravity acts instantaneously. If the Sun suddenly disappeared, Earth would instantly fly off in a straight line. The gravitational effect would be felt immediately across any distance. Einstein's picture is completely different. Its changes in the gravitational field propagate at the speed of light. If the Sun disappeared, we wouldn't feel the gravitational change for about 8 minutes, the same time it takes light to reach us. And when massive objects accelerate, they create ripples in space-time itself, gravitational waves, literal waves in the fabric of space-time, propagating outward at the speed of light. In 2015, the LIGO detector observed gravitational waves for the first time. 2 black holes, each about 30 times the mass of the Sun, spiraling into each other and merging. The collision was so violent that it radiated about 3 solar masses worth of energy as gravitational waves. Those waves traveled across 1.3 billion light-years of space and reached Earth as incredibly tiny distortions of space-time, stretching and compressing space by less than the diameter of a proton. And we detected them. We felt the geometry of space-time itself vibrating. This is something that Newton's gravity simply cannot account for. In Newton's theory, there are no gravitational waves because there's no space-time to wave. Gravity is a force that acts instantly. Einstein's picture predicts gravitational waves, and we've now detected them dozens of times. Each detection is a confirmation that gravity is geometry, not force. Now, let me talk about something that should really disturb your sense of reality. If gravity is not a force, then what is falling? When you drop a ball, what happens? In the Newtonian picture, the force of gravity accelerates the ball downward. In the Einsteinian picture, the ball is not accelerating the ball. The moment you release it is in free fall. It's following a geodesic through curved space-time. It is in inertial motion. It feels no force. If the ball had a tiny accelerometer inside it, that accelerometer would read 0 during the fall. Zero acceleration. The ball is not being pushed or pulled by anything. It's just going straight through curved space-time. The ground is what's accelerating. The ground is being pushed upward by the electromagnetic forces between atoms in the Earth's crust. Those electromagnetic forces are preventing the ground from following its natural geodesic, which would be to fall toward the center of the Earth. The ground is accelerating upward. The ball is not accelerating at all. And when the ball hits the ground, that's not the ball being stopped by a surface. That's the accelerating ground slamming into an inertially moving ball. This is a complete reversal of what you think is happening. You think you're standing still and things fall toward you. In reality, you're accelerating upward and things that are released simply stop accelerating and follow their natural path, which the accelerating ground then intercepts. Let me push this even further. Think about what this means for the astronauts on the International Space Station. They're floating, they're weightless. It's in the Newtonian picture. They're in free fall, constantly falling toward Earth, but moving sideways fast enough that they keep missing it. They're still under the influence of gravity. It's in Einstein's picture. The astronauts are doing nothing special. They're in inertial motion. They're following geodesics through slightly curved space-time near Earth. They feel no force because there is no force. They're just going straight. It's us on the surface who are doing something unusual. We're being accelerated, pushed away from our natural geodesic paths by the rigidity of the ground beneath us. The astronauts are in the natural state. We are in the unnatural state. Floating is normal. Standing on the ground is what requires explanation. Here's where things get philosophically deep. If gravity is not a force, but a property of space-time geometry, then what is space-time? What is this thing that curves and warps and vibrates? For Newton, space was just an empty stage on which physics happened, an infinite, flat, unchanging container. Time was a universal clock ticking the same everywhere. But in Einstein's picture, space-time is not a stage. It's a player. It's a dynamical entity with its own properties, its own behavior, its own physics. Mass tells space-time how to curve. Space-time tells mass how to move, the famous summary by John Wheeler. But what is space-time made of? What is this stuff that can bend and ripple? This is one of the deepest unsolved problems in all of physics. We know space-time is described by a mathematical object called the metric tensor. This tensor encodes the geometry at every point, telling you distances, angles, curvatures. General relativity gives us equations, Einstein's field equations, that describe how the metric tensor responds to the presence of mass and energy. But general relativity treats space-time as a smooth, continuous fabric, and we know that at very small scales, at the Planck scale, about 10 to the minus 35 meters, the smooth picture must break down. Quantum mechanics demands it. At the Planck scale, space-time itself should be subject to quantum fluctuations. It should be foamy, uncertain, probabilistic. But we don't have a theory that describes this. We don't have a quantum theory of gravity. This is the holy grail of theoretical physics. String theory, loop quantum gravity, various other approaches all attempt to provide a quantum description of space-time, but none of them is complete. None of them has been experimentally confirmed. We know gravity is geometry, we know space-time is dynamic, but we don't know what space-time fundamentally is. And until we do, we're missing something deep about the nature of gravity. Let me tell you about black holes, because they represent the most extreme example of gravity as geometry, and they reveal just how strange this picture really gets. Let's see. Black hole is not an object that sucks things in with tremendous gravitational force. That's the Newtonian picture, and it's misleading. A black hole is a region of space-time that is so severely curved that all geodesics, all possible straight paths, lead inward. Past the event horizon, every direction in space-time points toward the singularity, not just every direction in space, every direction in space-time. This includes the future direction of time. It's inside a black hole. The singularity is not a place. It's a time. It's in your future no matter which direction you move. You cannot avoid it, any more than you can avoid tomorrow. There is no force pulling you toward the singularity. There doesn't need to be. The geometry of space-time is arranged so that all paths lead there. Every geodesic, every possible trajectory, every attempt to move in any direction still takes you to the singularity, because the singularity is not below you, it's ahead of you in time. This is gravity as geometry taken to its ultimate extreme, and it reveals something about gravity that the Newtonian force picture completely misses. Gravity is not about objects attracting each other. Gravity is about the shape of the universe itself. Now, there's something else about gravity that makes it unique among the fundamental forces of nature. In particle physics, we describe forces using quantum field theory. The electromagnetic force is carried by photons. The strong nuclear force is carried by gluons. The weak nuclear force is carried by W and Z bosons. These are all quantum fields with force-carrying particles, and physicists have long tried to describe gravity in the same way. In this picture, gravity would be carried by a hypothetical particle called the graviton, a massless spin-2 boson. We can write down the theory of gravitons, at least approximately, and it works well for weak gravitational fields. But here's the problem. Gravity resists quantization in a way that no other force does. When you try to apply the standard quantum field theory techniques to gravity, you get infinities. It's uncontrollable, unrenormalizable infinities. The theory blows up. It becomes meaningless at high energies, precisely where quantum effects should matter most. This isn't just a technical difficulty. It's telling us something profound. Gravity is not like the other forces. The other forces operate within space-time. They are fields defined on the stage of space-time. Gravity is space-time. You cannot separate the force from the arena in which forces act. Trying to quantize gravity using the same techniques as the other forces is like trying to quantize the stage while the play is still running on it. It doesn't work because gravity is fundamentally different. This is why many of us in theoretical physics believe that the final theory of quantum gravity will require a radical rethinking of space-time itself. Not just a new force, not just a new particle. It's a new conception of what space and time actually are. Some approaches, like my own work on the holographic principle and the connection to quantum information, suggest that space-time might be emergent. That space and time are not fundamental ingredients of reality, but rather arise from something deeper, something related to quantum entanglement and information. If this is true, then gravity is not even geometry in the deepest sense. Geometry itself is an approximation, a macroscopic description of something more fundamental that we don't yet fully understand. It would mean that the question of whether gravity is a force or geometry is itself missing the point. Both descriptions might be different approximations to a deeper reality that is neither force nor geometry, but something else entirely, something we don't have a name for yet. But let me bring this back down to Earth, literally, because the practical consequences of gravity being geometry rather than force are not just theoretical curiosities. They affect how we understand our place in the universe. Consider this. Right now, you feel your weight, you feel the chair or the ground supporting you. You interpret this as gravity pulling you down, but now you know the truth. The ground is pushing you up. You're being accelerated. The comfortable, stable feeling of sitting or standing is actually the feeling of being accelerated away from your natural path through the universe. And here's the beautiful part. If you were to jump off a cliff for those brief seconds of free fall, you would feel weightless. You would feel nothing. No force, no pull, no push. For those few seconds, you would be in the most natural state of motion possible. Following a geodesic, going straight through curved space-time, you would be, from the perspective of general relativity, perfectly at rest. It's the ground rushing up to meet you. That's the violent event, not the fall. This inversion of perspective is what makes general relativity so revolutionary. It doesn't just give us better predictions. It doesn't just correct Newton's equations at the margin. It completely redefines what we mean by natural motion, by force, by acceleration, by the experience of weight itself. Everything you feel when you call it gravity is actually acceleration. And everything you would feel in the absence of a floor beneath you, weightlessness, free fall, that's the absence of acceleration. That's natural. That's how the universe wants you to move. We spend our entire lives being pushed away from our geodesics by the electromagnetic rigidity of solid matter beneath our feet. We have never, not for one moment of our lives, been in true natural motion. We are always being accelerated, always being pushed, and we call this normal. I want to address something that people always ask me. If gravity isn't a force, then why do we teach it as a force? Why do physics textbooks spend chapters on gravitational force, gravitational potential energy, gravitational fields? There are two reasons. The first is practical. For the vast majority of situations we encounter, Newton's description works perfectly well. You don't need general relativity to calculate the trajectory of a baseball or to design a bridge or to send a spacecraft to Jupiter. Newton's force picture gives you the right answer to extraordinary precision. It's simpler, it's easier to calculate with, and for most engineering purposes, it's all you need. The second reason is deeper and a little bit sad. General relativity is hard. It requires mathematical machinery, differential geometry, tensor calculus that most people never learn. The conceptual shift from force to geometry is enormous. It requires abandoning intuitions that are burned deep into our brains by millions of years of evolution. We evolved to understand forces, push and pull, throw and catch. We did not evolve to understand curved, four-dimensional pseudo-Riemannian manifolds. So we teach the simpler wrong picture first and hope that students who go further in physics will eventually learn the right one. But I think this is a mistake. Not because everyone needs to learn tensor calculus, but because the conceptual revolution of general relativity, the idea that what we call gravity is actually the shape of space-time, is one of the most profound insights in all of human intellectual history. And everyone deserves to know about it, even if they never solve a single equation. Let me tell you what keeps me up at night. We know gravity is geometry, we know space-time is dynamic, we know mass curves space-time, and space-time tells mass how to move, but we don't know why. We don't know why mass curves space-time. We don't know why space-time exists. We don't know what space-time is made of, or whether it's made of anything at all. We don't know how to reconcile the smooth geometric picture of general relativity with the discrete, probabilistic picture of quantum mechanics. These are not small gaps in our understanding. These are chasms, and they've been open for over a century. Einstein published General Relativity in 1915. It's now been well over 100 years, and we still don't have a quantum theory of gravity. We still don't understand what space-time fundamentally is. This is the longest unsolved problem in modern physics. And I think it's the most important because gravity is not just one force among many. If my argument is right, if gravity is really geometry, really the shape of reality itself, then understanding gravity is understanding the fabric of existence. Every other force, electromagnetism, the strong force, the weak force, operates within space-time. Gravity is space-time. To understand gravity fully is to understand the stage on which all of physics plays out, and we don't understand it. Not really, not yet, but we're closer than we've ever been. It's the connections between gravity and quantum information, between space-time geometry and entanglement, entropy, between black hole physics and quantum computation. These are some of the most exciting developments in theoretical physics in decades. I believe we're on the verge of a revolution as profound as the one Einstein started in 1915. It's a revolution that will show us what space-time really is, why gravity behaves the way it does, and perhaps, if we're very lucky, what the universe is made of at the deepest level. You know, when I first learned general relativity as a young physicist, I was astonished, not by the mathematics, though. The mathematics is beautiful. I was astonished by the sheer audacity of the idea that what we call gravity, this thing we experience every second of our lives, this thing that keeps our feet on the ground and the planets in their orbits, is not a force at all. It's the shape of reality. The universe is not a flat stage with forces pushing things around on it. The universe is a curved, dynamic, living geometry that tells everything in it how to move. And we, standing on the surface of a small rocky planet, feeling our weight pressing against the ground, are not feeling a force pulling us down. We're feeling the ground pushing us up, refusing to let us follow the path the universe has laid out for us. We spend our whole lives being pushed away from where space-time wants us to go. And we don't even notice, but physics notices. Physics always notices. So the next time you feel your weight, the next time you drop something, the next time you watch the moon cross the sky, remember what's really happening? No force, no pull. No invisible hand reaching across space, just the quiet, elegant curvature of space-time, guiding everything along the straightest paths through a bent universe. That's gravity, not a force, a shape. It's the shape of reality itself. And after 50 years of studying it, I still think it's the most beautiful idea in all of physics.